So essentially 3 upon dy by dx is 3 upon sin x cos x plus 4 cot x plus 14x upon x square plus 7. 1 upon sin x into 1 upon cot x can be replaced as cosec x cot x. And that is the sum. Have a look. It's a simple sum, a straightforward sum, easy flowing sum. But there are many steps that you have to take care of, many expressions, many formulas, whether it be of logarithms or of derivatives. So y is equal to sine inverse of 2x plus 1 upon 1 plus 4x. As per the tradition, I want to express y as sine inverse of sine of some function, because I know the inverse trigonometric function of the same trigonometric function of some expression is that expression itself. I also know sine 2x has two forms, or let's say sine 2 theta has two forms, 2 sine theta upon 2 sine theta cos theta, also 2 tan theta upon 1 plus tan square theta. You can safely rule out trying to express the bracket as 2 sine theta cos theta, because there is no denominator, we have a substantial denominator here. The question is, can I try and express it in the form of 2 tan theta upon 1 plus tan square theta? We can certainly give it a shot. Y is equal to sine inverse. I can write this as 2x into 2 raised to 1 upon 1 plus 2 square of x. Y is equal to sine inverse 2x into 2 raised to 1 upon 1 plus. Note very carefully what I have done. I know x raised to m bracketed n is x raised to mn. I know x raised to n bracketed m is x raised to nm. So I can say x raised to m bracketed n is equal to x raised to n bracketed m from these two. 2 raised to 2 bracket, the whole bracketed x I have replaced as 2 raised to x, the whole bracketed 2. It essentially is the same thing. Also, ऊपर मैंने क्या किया है? I have split x raised to m plus n as x raised to m into x raised to n. So 2 raised to x plus 1 has been split as 2 raised to x into 2 raised to 1, wherein I have considered x to be m, I have considered 1 to be n, and the x, which is the power or which is the base, to be 2. Now we say let 2 raised to x be tan theta. So y is equal to sine inverse tan theta into 2 upon 1 plus tan theta the whole square. So y works out to sine inverse 2 tan theta upon 1 plus tan square theta. Y is sine inverse sine 2 theta. Y is equal to sine inverse sine 2 theta. I am replacing 2 tan theta upon 1 plus tan square theta as sine 2 theta. Sine inverse of sine of anything is anything. So y works out to 2 theta. I'd assume 2 raised to x to be tan theta. So by my inverse knowledge, I can say theta is equal to tan inverse 2 raised to x. Thereby, y works out to 2 tan inverse 2 raised to x. Before I differentiate it, it's important for me to understand what is the differentiation of tan inverse x with respect to x. If u is tan inverse x, u dash works out to 1 upon 1 plus x square. v is tan inverse function of x, v dash is 1 upon 1 plus function of x square into f dash x. So y is 2 tan inverse 2 raised to x ddx of y is equal to 2 into ddx of tan inverse of 2 raised to x. Therefore, dy by dx is equal to 2 into 1 upon 1 plus function of x raised to square, 1 upon 1 plus 2x raised to square into d by dx of the function, which is 2 raised to x. I also know d by dx of any a raised to x is equal to a raised to x log a raised to x log a. So dy by dx is equal to 2 upon 1 plus 4 raised to x into 2 raised to x log 2. This 2 raised to x and this 2 raised to 1 in the denominator can finally be written as dy by dx is equal to 2 raised to x plus 1 upon 1 plus 4 raised to x into log 2. Have a look at the way the sum has flowed. In the later part, it's pretty much similar to what we have done. However, the initial separation and then substitution was slightly different than the earlier problems. Have a careful look at the steps minutely and try and get a better grasp of the same. Another sum, tan inverse 2e raised to x upon 1 minus e raised to 2x. Tan inverse 2e raised to x upon 1 minus e raised to 2x. Therefore, we let, again, this is of the form tan inverse. I want to establish it in tan inverse tan of a function, so I get the function itself. I know that there is only one expression for tan 2 theta. It is 2 tan theta upon 1 minus tan square theta. It's slightly similar to the sum we just did. I say let y be equal to tan inverse 2 e raised to x upon 1 minus e raised to x the whole square. Once again, using the law of indices, which states that x raised to m bracketed n is equal to x raised to mn. So let e raised to x be tan theta. Let e raised to x be tan theta. Therefore, y becomes tan inverse 2 tan theta upon 1 minus tan theta the whole square y becomes tan inverse 2 tan theta upon 1 minus tan square theta y becomes tan inverse tan of 2 theta. So y becomes 2 theta, and theta is nothing but tan inverse e raised to x if you rearrange. So y becomes 2 tan inverse e raised to x. 2 tan inverse e raised to x. What is, if u is tan inverse of a function of x, u dash is equal to 1 upon 1 plus function of x square into derivative of the function of x. So d by dx of y is equal to 2 into d by dx of tan inverse e raised to x. Therefore, dy by dx is equal to 2 into 1 plus the function of x square into derivative of e raised to x. Therefore, dy by dx becomes 2 e raised to x upon 1 plus e raised to 2x. Fairly simple sum, pretty much similar to the earlier sum we did of in the form of sine inverse, a different kind of a substitution. I'm fairly sure that inverse trigo का अब तक अच्छा grasp आ गया होगा, because we have done plenty of problems and different kinds of problems. So have a look at the problem. Let's go ahead. If y is equal to root of plus root of plus root of all the way till infinity, all the way till infinity. So you have to prove that dy by dx is equal to sec square x upon 2y minus 1. I can write y as under root tan x, जो भी है आगे additions, root of tan plus something, the same form from which y, the RHS of y itself is starting. So for the rest of it all the way till infinity, I can simply replace it as y. It's ultimately a repeated addition of y. So if y is equal to root of tan x plus y, and if I differentiate both sides with respect to x, I get d by dx of y is equal to d by dx of root tan x plus y. So dy by dx works out to 1 upon 2 root tan x plus y into ddx of tan x plus y. dy by dx works out to 1 upon 2 root tan x plus y into, what is the derivative of tan x? Take separately. ddx of tan x plus ddx of y. dy by dx then works out to 1 upon 2. Can I replace root tan x plus y simply as y? Absolutely I can. I'm writing instead of root tan x plus y simply a y. Derivative of tan x with respect to x is sec square x. Derivative of variable y with respect to x is dy by dx. If you cross multiply 2y with the LHS, 2y dy by dx is equal to sec square x plus dy by dx. Take the dy by dx with the RHS to the LHS. You get 2y dy by dx minus dy by dx is equal to, can I take something common on the LHS now? dy by dx into 2y minus 1 is equal to sec square x. Therefore, dy by dx is equal to sec square x upon 2y minus 1. That's the sum for you guys. Have a look at the sum. A very important sum, the next one. If x minus a square plus y minus b square is equal to c square, prove that 1 plus dy by dx square the whole to the power 3 by 2 upon d square y by dx square is a constant independent of a and b. Any constant but independent of constants a and b. Let's see. Part 1 of the sum. I have x minus a square plus y minus b square is equal to c square. I can differentiate both sides. What happens? D by dx of x minus a square plus d by dx of y minus b square is equal to d by dx of c square. This effectively becomes 2x minus a raised to 2 minus 1 by the x raised to n formula plus 2y minus b raised to 2 minus 1 into ddx of y minus b. I did not do ddx of x minus a because d by dx of x is 1, d by dx of a is 0. I presume by the end of derivatives you would have understood that much. D by dx of y minus b, because I know ddx of y will work out to something else, although ddx of b will again be a constant, and ddx of c square is definitely a constant. So 2x minus a plus 2y minus b into dy by dx is equal to 0. If you take 2 obviously goes off. If you take x minus a on the RHS, y minus b into dy by dx is equal to negative x minus a. dy by dx is essentially negative x minus a upon y minus b. That is part 1 of your sum. Let's do part 2. dy by dx is equal to minus x minus a upon y minus b. Let's try and differentiate it once more. Negative sign बाहर रख रहा हूं. ddx of x minus a upon y minus b. Here the d by dx of u by v rule, which is v u dash minus u v dash upon v square, is applicable. D square y by dx square works out to y minus b into u dash ddx of x minus a minus x minus a into ddx of y minus b. V u dash minus u v dash upon y minus b square. So d square y by dx square is equal to ddx of x minus a is 1, y minus b minus x minus a into dy by dx upon y minus b the whole square. D square y by dx square is equal to y minus b minus x minus a into minus x minus a upon y minus b. What have I done? I've just replaced dy by dx by statement 1. With my finding from statement 1. The whole upon y minus b the whole square. If you rearrange, what happens with your d square y by dx square? D square y by dx square works out to y minus b the whole square in the numerator. Minus minus becomes plus, plus x minus a the whole square. The y minus b and the y minus b square in the denominator get adjusted and become y minus b the whole cube. Y minus b the whole cube. Y minus b square plus x minus a square, as per the question itself, is nothing but c square. So my d square y by dx square is equal to c square upon y minus b the whole cube. I call this as statement 2. Finally, part 4 of the question. What is asked? 1 plus dy by dx the whole square, numerator is to the power 3 by 2 upon d square y by dx square. ये जो भी computation है should be a constant independent of a and b. What is dy by dx?